Morning, and thank you for joining us. Today's webinar is on mercury analyzers for today's lab thermo-decomposition HG analyzer, presented by Jeff Forsberg, our product line manager. We will be taking questions throughout the webinar, so feel free to submit those, and I will go ahead and turn it over to Jeff.
Thank you, Shelley. Welcome, everybody. Again, thank you for sitting in on this continuing education series regarding our mercury systems. Today, I have a short presentation that describes the theory of the Hydra II thermal decomposition mercury analyzer. It's a direct mercury system for solids, semi-solids, and aqueous samples. And let's get started. So, if any of you are new to this type of analysis, this goes back to 1968. Hatch and Oates started the first cold vapor atomic fluorescence system, atomic absorption system, directly on the following the commercially available AA systems that were hitting the market about that time. And shortly after that, it quickly became the reference technique for pretty much all mercury analysis. And then in the early 80s and late 80s, atomic fluorescence came on board with some crude commercial devices. And then in the 1990s, we had atomic fluorescence with and without gold that was available for commercial use. So a little bit about us. We've been in business for more than a quarter of a century, manufacturing and mercury analyzers. So back in 1991 it started, and throughout the years we've upgraded our systems and introduced new systems. And recently in 2017 we introduced the new auto samplers with the quick trace systems. These are composite auto samplers, more robust, and also corrosion and things like that are more controlled with these new auto samplers. So a little bit more about Teledyne Leeman Labs. We develop instruments that satisfy most of your mercury analysis needs. We give you a choice of mercury analyzers within your laboratory to fit your needs. And then all our systems are based on cold vapor atomic spectroscopy with or without gold enrichment, which is gold amalgamation or gold trap analysis. So we have two lines, the Hydra II and the Quick Trace product lines, and they cover a variety of techniques and digest matrices. And they also meet the requirements, the quality control requirements that can be quite stringent depending on the methodology for US EPA and European norm methods. Our customers include environmental labs, academics, petrochemical, food, mining, agriculture, energy, pharmaceutical, nutraceutical, water, and wastewater. Basically, if there's a lab bench in that facility and they're analyzing for mercury, you'll find one of our systems in that facility. All right, so now let's get to the thermal decomposition. So thermal decomposition mercury analyzers, they're created and or manufactured for direct determination of mercury in solids or semi-solids, direct determination of mercury in at the ppb level in aqueous samples. So there's no time-consuming or complex sample digestion steps. Is really a nice feature. There's no wet chemistry for the solids and semi-solids, but we do have to add a stabilizing solution for the liquid samples or the aqueous samples. I use 100 microliters of 0.03% L-cysteine solution. It also eliminates toxic waste disposal. The only thing you really need to dispose of is the ash that comes from the sample boat. And it's really fast, approximately 5 minutes per sample, depending, well, it kind of depends on the sample type, but we can average it up to about 5 minutes per sample. So thermal decomposition, it's mass-based. So it's sample matrix independent. You don't have to worry about what type of samples they are, again, because it's mass-based. It's based on the calibration is nanograms of mercury. So we use one calibration for most sample types. The standard operating condition can also be applicable to most of those sample types. And we run multiple sample types without operator intervention. Again, like I said, fast turnaround, about 5 minutes per sample. So some of the applicable methods, and these are used pretty much throughout the world. So we have US EPA 7473, and different regions use some variation of these methods, but the basic method is what I refer to when they're used throughout the world. ASTM 6722, which is coal and combustion residues like fly ash, coal ash, and different things like that. That's what that method was developed for. And then ASTM 7623, which is for crude oils and petroleum products and items like that. But the main one is 7473. That's what would be used in most laboratories for analysis of fish and soils and semi-solids and items like those. So how does it work? Well, it's kind of neat and it's pretty simple. So we have basically 7 steps. We have load, inject, dry combust, purify, remove moisture, collect, dilute, and detect. So with those 7 steps, our dynamic range is 0.05 to approximately 1,500 nanograms. And again, there's no pre-treatment of the sample. So you combust it, and then the elemental mercury is concentrated on a gold trap. And again, we don't use any stannous chloride, no sodium borohydride, so there's no reducing agents. And the incident light is 253.652. So again, it's 7 steps: load, inject, dry combust, purify, remove moisture, collect, elute, and detect. And now I'm going to focus in on each one of those steps so you can get a better feel for how the system works. So in the beginning, you weigh a sample, and then that sample is introduced into the system. And you can introduce it manually, or you can use a sequence. The sequence is controlled by the auto sampler, and it'll pick up the samples and inject them into the decomposition furnace. So once they go in there, typically we have oxygen flowing, but it depends on your sample type. You can use air, but there's oxygen flowing or air flowing over the sample, and then the furnace is going to elevate its temperatures. First, to dry the sample, so we bring it up to a max of some temperature. Typically it might be 300 degrees C. And then once the sample is dry, and this is kind of based on experiments with the system as well, so you kind of know your samples, and we have methods that are set up so you know what time and temperature at dry stage it needs to be sufficiently dried. So once that's done, then the temperature again is elevated to a decomposition phase. And typically it's about 800 degrees C. You can go up to 1,000, but most analysis about 800 degrees C is going to give you a good thorough decomposition of that sample. So once that happens, now this is the purify step. So the gases from the decomposition are carried through the catalyst. And the catalyst is a proprietary mix of chemicals, and it's going to remove the halogens, the nitrogens, and those oxides of those, and then also the sulfur oxides. So anything that could foul the gold trap and or the detector system are removed here. Then we have a pretty much clean gas that's just laden with mercury and water vapor, and that leaves the catalyst, and then that goes into our moisture removal system. It's a Nafion dryer system, and Nafion will hold about 20 times its own weight in water vapor, and there's also a counterflow. So inside the membrane we have mercury with oxygen gas flowing through, and then on the outside of the membrane we have a counterflow. It could be argon and or oxygen, but typically I like to use argon because it saves on the oxygen use. That will pick up the water vapor and remove it from the pores of the membrane, and then that sweeps it out the back of the instrument. So out of the back of the instrument, you have argon, if that's what you're using, and water vapor that's removed from the sample. And then from there, it goes on to the gold trap, where it is captured at the gold trap, and it lets the other gases flow through, and it flows. It's linear system at this point, so it flows right through to the detector and then out to waste. At that point, the gold trap is heated, and then that'll release the elemental mercury into the carrier gas, and that transports it and transports the gas to with the mercury in it to the spectrometer. From there, in the spectrometer, we have a two-peak detection system set up. So we have two 5-inch cells that are mirrored, so the light travels through two 5-inch cells. So effectively we have a 10-inch cell, and that's for low concentrations. And then we have a 1-inch cell for high concentrations. So the mercury will flow through both those cells, and the light travels through both cells, and then the transient signal is measured by the AA detector, and that's step 7. So when we're going through two cells, we integrate two separate peaks, and the integration is reported against the best calibration of those two cells. So the best calibration fit for that peak is what the system will automatically use in the report. Here I have an example of the two cells, and it's a 1 nanogram per liter at 5 mils a sample. So it's a 1 ppb solution, 5 mils a sample, and it's actually an aqueous sample in the system. And it shows you how we provide two peaks. So for example, if this peak was outside of the normal linearity of the first peak, the one that's green right here, then the second peak would be what would be reported on the report, because that would be within the linear range and within the calibration constraints of the system. So here's some typical competitive published instrument detection limits. So what do they mean for us? What do they mean for you? So AA is anywhere from 1 to 5 ppt. AF is anywhere from less than 0.1 to maybe 0.2 ppt, and AF with gold typically reported at less than 0.05 ppt, nanograms per milliliter for AF gold. The thermal decomposition depends on the system and kind of how they fall out. So we have 0.01 to maybe 0.005 nanograms. Again, it's a mass-based system. So what do we do? So an example of what does that mean for us is, how do we calculate MDLs from this for solids? So it's quite simply, you just take the mass of the estimated detection limit. So let's just assume that in our case it's 0.002 nanograms, and we have a 0.2 gram sample. So it's simply the instrument detection limit, 0.002, divided by the mass of the sample, and that's going to equal 0.01 nanograms per gram, or else ppb. So that's my theoretical method detection limit for this system, and it all depends on a number of factors, gas flow and different things like that, because you can kind of tweak the system out to change the dynamic range. So that's why this one is at 0.002. So again, the Hydra IIC is basically designed for 74, 73 and the other two ASTM methods, but it's not really recommended for trace level determinations in water because the method detection limit is around 0.1 ppb, but that's not bad, but it's not really trace. And so the system is superior to liquid digest is regarding detection limits. So let's look at it this way. Let's assume that we have a nominal instrument detection limit of 0.001, and again, it's based on some of the parameters of the system, gas flows, and different items like that. So let's assume 0.001. Now, if we take that value and we use a 0.2 gram sample, my detection limit or typical method detection limit would be 0.005 nanograms per gram. If I up my mass, then it drops it down. So now at 0.002 at a half a gram sample. Now, when we compare these to liquid digest, they're far superior. So a 0.002 nanogram per gram, a 0.005 nanogram per gram, when I do a comparative against a liquid digest, that would be 0.05 and 0.02 ppt nanogram per liter, and that would be based on a half a gram sample and a 50 ml digest. Now, if we look at those values, 0.05 and 0.02 ppt nanogram per liter, that's really, really hard to do. There isn't a lot of systems on the market that run liquid samples that can hit those type of detection limits. You have similar detection limits at 0.05 for some of this clean analysis like EPA 1631. Maybe even closer to 0.1, but it can be down to 0.05 depending on your values that you're using for the solution, so the uptake volumes, I should say. But it's very hard to do. So in that case, running a solid system that combusts solid samples, it gives you a far superior detection limit than if you were doing digest. So it's really, really a fabulous system. And if you're really into trace analysis for solids, it's the only way to go. But with that said, yes to aqueous samples. So US EPA Solid Waste Digest 846 Method 7473 is promulgated for mercury determination by direct combustion. And that method is for solids and solutions. By default, that's how it's written, and it works for those methodologies. So if you're in an environmental laboratory and your sample load is a lot of solids and your liquids are, say, 10%, but your solids are 90%, maybe this is the system for you. You can eliminate that digest. So aqueous analysis, here's a precision study, an MDL study. So at a 1 ppb solution, the percent RSD was 9.2, and my sample was N equals 30. The instrument detection limit was 0.104 ppb, and then that's based on a 95% confidence level from CFR 40 136 Appendix B. That's a two-stage detection limit where you run two different sets of concentrations, and then they do a pooled standard deviation. You also have to meet certain criteria for an F ratio. It has to be less than 3.05 in order for the MDL to be valid. So how does this system improve my protectivity? Well, dry samples, from sample in to numbers out, it's about 5 minutes. Wet samples, about 7.5 minutes. Aqueous samples, about 8.5 at a half a mil. The dry stage is increased. Obviously, you have lots of water to deal with, so it's 3.5 minutes for the dry stage. And again, the MDL is around 0.1 ppb. 70 samples, But with the 70 sample capacity, we have something we call virtual. So we can add sample racks and just keep going. It's really a neat feature, and I'll get into that in a couple slides, so you'll see kind of how that works. So time-wise, it's about 60 samples in approximately 5 hours. If we compare that to reduction, 60 samples is still about 5 to 6 hours with digesting, cool down time, and then your analysis time, but it's kind of method dependent. So when we compare the analysis times, we can just forget about the weigh time because the weighing has to happen for both. For running aqueous digest, you still have to weigh the sample, and you still have to weigh the sample for a combustion, so we'll just eliminate that. Now, the reduction does become faster after 60 samples, but that's only if you are totally looking at just the analysis time, and you exclude the digestion labor and if you have multiple digestion blocks. So after 60 samples, just the analysis time, yes, of course, liquid samples are faster because you can run them from 60 to 120 seconds per sample where, so it's like 2 minutes where this one takes 5 minutes at the very best, maybe 4 minutes to run a really dry sample. So when is it most useful? So this type of system is extremely useful, like I said, if you have a lot of soils, sediments or sludges, coal, fly ash, and if you want to analyze fish without having to digest them, this is the tool for you. Foods and feeds, plants and tissues, and ores. Or if you have difficult samples that are difficult to digest, you might want to run it on a combustion system. And or samples with known chemical interference. There is a few interferences that can't be compensated for by a liquid digest. So here's an example of a couple. So thermal decomposition will eliminate most of these type of interferences. Here's one on the left with potassium iodide, and as you see, the percent increases from 1 all the way up to 3%. The response basically drops off to 0, and this is with atomic fluorescence system. If we go over to the right, here's a gold solution, and as the concentration increases in ppms from 0 down to 100, the response by atomic fluorescence basically drops to 0. On the top of the graph, you'll see the response for the combustion system. It's pretty much a steady state. So the matrices within that sample isn't affected in the direct composition system. So sample types, so a variety of samples, again, without matrix issues. Again, in its one calibration size, basically fits all. So we recall calibrations, and you can reuse the same calibration over and over again until your quality control starts to fall out. And that usually indicates that you may have some maintenance that needs to be taken care of, such as changing the catalyst, maybe changing the gold trap, and looking at the drying system, and a couple of those items to get the calibration back where it should be. But once you recall a calibration and pull it up with your method, you just simply run a couple of quality controls checks, one in each calibration zone, one for the high concentration samples and one for the low concentration samples. And if they fall within their quality control criterion, then you just go with the samples and you're ready to rock and roll. So over on the left, I have a calibration that is 0.993, and it's made up primarily of sediments and fish and tissues and things like that. And then over on the right, we have some typical samples that you may digest and run on a liquid system. So if you look at the recoveries, the worst recovery is 11.7% above 100, so 111.7. So this is nothing outside of the norm that you would see on recoveries for liquid samples that run through a complete digest process, and when they're based back against their certified reference values, they're usually within the plus or minus of that value. So again, it's really, really nice, and it looks really good. So anywhere from liver to blood to dogfish, oysters, sediments, and coal, they're all within their specified recovery limits. Now let's talk a little bit about the software for the Hydra IIC. So when you open up the software, there's basically three subtabs. You have method, sequence, and analysis, and they're across the bottom right here, and that's where you run the system from. On the top, you have Run, View, Tools, Help right across here. Those are consistent with each tab. They don't change. So on the left, I show what the drop-down menu would look like under each condition. So we have method, and then sequence, and then analysis. So right here, it changes what's displayed from method to sequence to analysis, and View, Run, Tools remains the same. So under method, that's where we have instrument controls, and those are global settings. I'm going to speak a few slides down about adjusting individual parameters for samples. It's really easy to do, so each sample can have its own setting, but these are global settings. So they control the injector, the auto sampler. So here you can exercise the injector, you can send it home, you can move the elevator, you can close. It gives you a readout of what rack you're on and what's the sample location. Gas control, you can change your gas control here. The integration time for your detector, the dry temp, decomposition temp, catalyst temp, the lamp off and on, and the amalgamator temperature, the gold trap temperature. And then also you have the calibration. Also from this menu, the drop down is new, open, rename, save, and close, and exit. So you can pull up a method that you really, really like and you want to tweak it out a little bit. You can clone it, and then you can add or subtract standards to tweak that method. It's really a nice feature, the clone. A little bit about the calibration. So again, we have two cells. We have the 10-inch cell, and that's for low calibrations or high sensitivity, and then we have the short cell, which is for higher calibration concentrations and or low sensitivity. So the typical range for the low calibration range is around 20 to 30 nanograms, and again, this is mass-based. You can run linear, quadratic, weight-fitted, and you can pick and choose calibration points, and you can have multiple points for the same mass. That's allowed. It's not an issue. And then you can select or deselect points. So again, it's linear, quadratic, or weighted fit calibration. And here you can exclude or include points. You just highlight on the standard that you want, and then once you do that, another option opens up where you can exclude. So the high range, or the high calibration range, typically 1,000 to 1,500 nanograms. And the same thing, a linear, quadratic, or weighted fit. This is a quadratic fit here because atomic absorption, once you hit maybe 400 to 450,000 microabsorbance units, or 0.4 to 0.5 within that range, absorbance units, you run nonlinear. And this is true for any system that's absorbance-based. So you start to hit that nonlinear function at those values. So at that point, you really need to run quadratic fit. So here we're calibration up to 1,000 nanograms, and it's quadratic, and the correlation is 0.9989, I believe. And again, you can run multiple points at the same mass, and you can select or deselect calibration points. So once the calibration is done, you can accept single points. If there was a problem with a standard or something just doesn't look right, you don't have to select it, or you can accept all. So again, that's post-calibration, accept a single or accept all, and then also post-mass point additions or mass point deletions. You have to re-accept that point or that calibration. You can clear the calibration, you can delete the calibration, and you can print the calibration graph. So you have a lot of options from the instrument page on the calibration. A little bit about the sequence page. I mentioned earlier about the virtual samples. So here on this screen, this is where you take care of those functions. So if we look at the top, the hot buttons up here, this is where you can cut, copy, paste, auto renumber, fill down. There's a lot of features within here. You can click on the arrow left or right that's to the right here, and that gives you control over your enter. So it'll either enter down or enter left. And if you go enter left, it'll go from row to row. When it hits the end of the row, it'll go to the next row down. So this is for reviewing your times and your temperatures of each sample to make sure that you have what you want for that individual sample. Also, you can click on the screen here where the test rack is and the sample boats, and you right click and you can say start from here. So you can start with anywhere in the sequence for that sample, anywhere in the sequence. In the drop down menu here is new, open, save, print, exit. So it's pretty much similar to what the menu drop down is. So you can open a recall a save sequence, or you can create a new one, or you can save it or print it. So you can take it and take it to the hood and load up the samples into the boat shuttle. So on the sequence tab, this is where we can customize the time profiles and temperature profiles for each sample. Remember when I spoke briefly about the method and the instrument control? That's global. And then once you load a sequence, those global settings are populated in the sequence. But if you want to change the setting, it's really, really simple. So sample type, that's a drop-down menu for standards unknown, QC stop, preload, and update standard, that's in there. And then from there you can customize the temperature profile and the time. So on the dry time, it's a drop-down menu. Once you put your cursor in there, you have a drop-down menu anywhere from dry temperature anywhere from 0 to 500, decomp anywhere from 400 to 1,000, and then the elute time is anywhere from 30 to 60 seconds. The elute time is the time on the gold trap that the gold trap heats up and sends the sample off to the spectrometer. All those can be really easily customized per sample. So it's really a nice feature, and you have a lot of options to control your analysis for the solid, semi-solids, or aqueous samples. And in order to see the full menu on this screen, there's a lot of information, so you really need to scroll back and forth to see it. On the analysis time, this is where, analysis tab, this is where we're viewing the results. You also have option for control charts, the report, recalculation of the data. You can show data, that's the raw data, and the CSV highlighted. You can highlight a sample. It can export the raw data for that sample. You can also print a screen. So this is an example where I have a 50 ppb check standard here, and then it's showing the data for all the samples below it. Now if I click on show data, now I'm going to look at that sample by itself. Some data points, each second or time, the raw intensity, the scan microabsorbance units, the regions for the baseline and peak microabsorbance units. It's going to show those as well, the background, and then the peak absorbance units as well, and then the corrected peak values. So on the very top of this page, if we scroll up, we would see the corrected peaks, and this is what's printed on the report. Now this is actually the peak values here of one of the calibration points, either I believe it's in the sensitive cell as well. So it shows you in real time each data point, how it increases in response, and then how it's calculated everything under the curve. So you can take this data and you can export it to Excel, and you can manipulate calibration graphs and for reporting, for Excel, for presentations. You can do a lot of things with this data right here, since it's so inclusive and it reports all the raw data. So on the analysis tab, under reports, you have 29 selectable fields. So down here, if you scroll down, there's 29 different fields you can choose from. And then you can report detailed or LT. LT is long-term statistical report. So if you're monitoring a control sample or something like that, that would also be reported here. And then you have recalculations. So under recalculations, you can change the weight, and then you can recalculate that sample concentration. So, but there's audit controls, so everything is reported into the audit features of the software. So if anybody wants to go and look at the control history of the sample, that's all available. So it's part of the tools available for a CFR Part 11, CFR 21 Part 11 analysis. On the analysis tab, we can also exclude or include or exclude all the samples. You can also rename the samples, and then there's a rename history. So you can click on that, and you can also get the rename history, and that's also uploaded to the audit trail as well. So if you're worried about having some of these controls, you need not worry, because everything's reported in. It also, when you change a sample, it puts a little red box around it. So when you're looking at the report or the analysis screen, you can tell that something has been changed on that sample. So you can go to the audit trail and you can view exactly who changed it, what was changed, and when it was changed. So there's some nice features for pharmaceuticals and nutraceutical type compliance. Multi-injections. So this is not limited. So under the sequence, under sample type, you pull down preload, and then you add the weight. So the analysis of each preload is going to collect them all in the gold trap, and then the final sample past the preload, which is right here, that's when it's going to elute it off the gold trap, and it's going to calculate that final concentration based on the sum weights. So the sum weights of all the preloads are added up, and then it's going to be the response. It's going to put it on the curve, and it's going to divide it by the mass of the sum weights, and that's going to give you your concentration. Now, just a short talk about the view and the run. So, and again, these don't change between analysis, sequence, and method subtabs. This is all the same. So view, you can view all chapters, the latest chapter. You can search by date range. And then under the run, the standard, check standard, and sample, that's manual. So you can click on one of those. You can load the standard, check standard, and sample up and hit go. Or else you can run the sequence. You can also run a proprietary sample, which we call the stat sample. If you click on that, and then you can load it up, and it'll put it into the report, and then you can stop. And again, this is the drop-down menu. It doesn't matter where you are. If you're method, sequence, or analysis, you get the same. So the tools is really a nice feature. So in there you can change user accounts. You have some database management tools. You have your events log, your audit trail, your sequence, schedule maintenance, your sample conveyor, and some instrument diagnostics where you can check out the system and make sure it's functioning properly, and you can pull some of that information and you can add it to your offline logbook. So if something starts to go foul on you, you can quickly track it in your logbook going back in time and see when it started to change, and that might help you with some of the maintenance on the system as well. The standards library, that's where you create the standards, and then also the check library, and then that's loaded into the sequence by standard name and weight, and then the system will look at this library and it'll know what standard's being run, so it can tell you what the mass is in nanograms into the calibration. And then also, I forgot to mention, on the calibration, you have the calculated concentration, so you know how far up or below you are from the actual reported mass of the system. So for example, if you think you have a 1 nanogram sample in that calibration, based on the calibration, it might be reported at 0.95 nanograms or maybe 1.10 nanograms or something on that effect. And then you can also search for samples. And then the help is typical help files, HTLM, and then startup files. You have the ionization file or initialization file, I should say, for the system. There's a lot of features in that file where you can tweak out your system to have it run a specific way. Favorites bar. So on the favorites bar, you have some of the same functions that you could hit on the pull-down menu. So you can run a standard, you can run a check standard, and these are just a hot button. So you can run the sample, run the sequence, pause. You have your stat sample here. Here you can go to user login. You have your audit trail. You can search for samples. You stop it. You have your help file. You have your startup. And you can put it in standby, sleep, and of course the maintenance and interlock. So click on the maintenance button and it'll bring up your maintenance screen and tell you how many shots are left on the gold trap, how long the catalyst potentially could last for, and different items like that. And here's the maintenance screen right here. So from the favorites bar, you click on the maintenance tab, and then it's an online maintenance. And then also, if you needed to replace something or have some maintenance performed on the system, there's a step-by-step instructions on the system. Once you click on the maintenance item that you want to address, it will take you through step-by-step instructions of how to mitigate the problem or address the maintenance or change the catalyst or whatever the problem might be. It kind of guides you through it. So it's really a nice feature. So in summary, the Hydra II systems are applicable to most of your combustion applications. They're far superior in detection limits for solids and semi-solids when compared to aqueous digestions. And they're really easily maintained, and hey, I think they make analyzing samples fun and worry-free. So a little bit about the other products. So we kind of offer a tiered approach. So we have the Hydra II AA, which is the entry-level reduction system, and the 7600, which is our higher-end cold vapor atomic absorption. And new this year, like I mentioned earlier, we have auto samplers and a new enclosure that goes with the M8000 and or 7600, the quick trace products. And then we have the Hydra IIC, and that's also cold vapor atomic absorption. So up next in this continuing education webinar series, my next webinar, I'm going to open up the Envoy software. I'm going to give you detailed features of how to accomplish the tasks that you desire in that software. And then coming soon to a webinar near you, I'm going to look at webinars for method development. I'm going to show you how to make standards and also method development with minimal sample preparation. We'll look at detection limits, aqueous analysis, and how are we compliant with some of the standard methods like EPA 7473, 7623 from the ASTM and petroleum distillates, and then also we'll look at the coal and the fly ash method 6722. Anyway, so that's some of the future webinars that you'll see coming your way. So if you want to learn more about the software, that's the one that's coming up next. So with that, that concludes our short webinar today on the introduction to the system, and we'll open it up for questions.